On behalf of 24houranswers.com, I welcome you to today's lesson. In this video, we're going to look at a real-world introduction to the derivative, one of the most important things you'll learn about in Calculus 1. And all we're going to do in this video is a little bit of algebra, a little bit of slope, and then towards the end, when we answer these questions, it's going to be a lot of repetition, but it's important to understand this. The final question down here is really going to be talking about the derivative, and one of the main applications of a derivative that you will run across is instantaneous velocity. In this case here, we have a rock. It's dropped from a 100-foot cliff. Its height h can be modeled by the following function based on time t seconds. So we have some function here, and basically we can plug in some time t seconds, and we can figure out how high the rock is off the ground. Now, what I've done over here for simplistic purposes is I've plugged in a few of these numbers. At time t equals 0, well, that's when the rock hasn't even been thrown yet, so its height is going to be at 100 feet because it's getting thrown off of a 100-foot cliff, as mentioned at the beginning of the problem. 1 second after it's been dropped off the cliff, its height is 84. 2 seconds, it's going to have a height of 36 feet off the ground. 2.25 seconds, it's going to be 19 feet off the ground, and so forth. The height is decreasing because we dropped it off the cliff. Question number 1, find the average velocity of the rock over the entire time it falls. Well, that means we need to figure out how long does it take for the rock to hit the ground. What we can do there to help us out, we can set the height equal to 0, and we can solve this equation. This equation here will tell us the amount of time it takes for the rock to hit the ground. When the rock hits the ground, that height, that h of t, is going to be 0. So let's solve this equation. Subtracting 100 from both sides, we get negative 100 equals negative 16t squared. Divide both sides by negative 16, you will get 6.25 is equal to t squared. And now let's take the square root of 6.25, and you'll get t equals 2.5 seconds. It's going to take the rock 2.5 seconds to hit the ground. We don't worry about the negative 2.5 since we're talking about a positive time t, the length of time after it was dropped off the cliff. This is helpful now because we can find the average velocity of the rock over the entire time it falls. The average velocity is going to be equal to the slope of the line. What line are we talking about? Over in Desmos, we're trying to figure out the slope of the line from here, that's when the rock was dropped, to here, that's when the rock hits the ground. So I want you to imagine a line, and it's called a secant line. The secant line goes through more than one point on a curve, and if we drew a line here, it would be going through these 2 points. What is the slope of that line? The slope of that line is the average velocity over the entire time interval that the rock was in the air. So to find the slope of a line, we do y2 minus y1 over x2 minus x1. So what am I talking about? What is my y2, y1, x2, x1? We're talking about two dots here, or 2 points. One point is at 0, 100. That's when the rock was initially at the top of the cliff. And then at 2.5 seconds, we knew the rock hit the ground. So at 2.5 seconds, the height of the rock would be 0. These are the 2 points. Let's plug them in. y2, I'll let that be 100, minus y1, which is 0, divided by x2, which is 0, minus x1, which is 2.5. Subtracting this, we get 100 over negative 2.5, and then dividing this, we get negative 40, and this will be feet per second. The reason why it's negative is because velocity has 2 pieces to it. It has a speed and a direction. Since the rock is falling down, that's the negative in our velocity, and it's falling at a rate of 40 feet per second. The negative simply means it's moving down. Let's repeat this process for the average velocity from t equals 1 to t equals 2.5. Then we'll do it from 2 to 2.5 and 2.25 to 2.5. Maybe you notice the 2.5 is getting used constantly here. That's a good thing because that means we can use the 2.50 in our slope. The only thing we're going to be changing is the first piece. So for question 2, our ordered pair for t equals 1 will be 1 second. And if you plug 1 into the function, I have it written right over here, but after 1 second, the rock's going to be 84 feet off the ground. After 2.5 seconds, we know the rock is going to hit the ground, or that's when the rock hits the ground. Let's do that same thing for average velocity. So doing this same exact formula, y2 minus y1 over x2 minus x1, we come up with negative 56 feet per second. And what I want us to start noticing is that here, initially, our time interval from 0 to 2.5 seconds, that was a 2.5 second time interval. Now this time interval here is only 1.5 seconds because we're going from 1 to 2.5 seconds. Look at our time interval here. It's getting shorter and shorter and shorter. And this is where I want you to maybe start thinking about a limit. But for now, let's go ahead and compute this slope, this slope, this slope, and let's slowly build up to these down here. And I'm trying to get you to notice something. And if you sit here and work through these, what you're going to realize it's the same formula every time. And if you recall, we're really just subtracting 0 up top. So all you have to do is take the y values that you get from each time interval. For example, from 2.25 to 2.5, I did my 19, as you can see there. And then since we have the x2 minus x1, if you take 2.25 and subtract 2.5, that's where I'm getting the negative 0.25 from. For sake of time, and since this is mainly an algebra review, I've also listed the 2.4 to 2.5 seconds. Notice our time interval is only 1/10 of a second. Now we have 100th of a second between these two, and then finally we have 1,000th of a second. But what I want you to notice is look at these numbers. I mean, back at the beginning, the average velocity was negative 40 feet per second. Then it went to negative 56, negative 72, negative 76, negative 78.4. And then once you get to here, notice it looks like this number's getting really, really close to negative 80. It turns out that is our derivative. That is what we call our instantaneous velocity. So, an educated guess, but it is going to be correct here, and we will see that in future videos. We can find this really fast once we learn how to find derivatives. But for now, I want you to think about a limit. What is this average velocity getting close to? And look at the question. How fast was the rock moving at the instant it hit the ground? Right there, that's only 1,000th of a second difference between those two time intervals. That rock was approaching an instantaneous velocity of negative 80 feet per second. And at that instant when the rock hit the ground, that's how fast it was moving. Obviously, once it hits the ground, it's going to be 0 feet per second because the rock is stopped. But this is the idea of a derivative. A derivative really involves us looking at a slope. Now, I mentioned the word secant slope back at the beginning, but what we're ultimately going to be finding and what the derivative is actually the slope of the tangent line. More on that soon, but I wanted to review slope, the y2 minus y1 over x2 minus x1, and we took our time intervals here and we shrunk them down. We kept these two pieces. We let them get closer and closer together, and hopefully you are familiar with a limit now, and it looks like this number is getting really, really close to negative 80. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.